And please bear with me for a moment while I do that. Uh, all right, folks, welcome to us to Support Vectors meetup. We do weekly paper readings. A very warm welcome to all of you. As always, please indulge me with a minute of a spiel about Support Vectors. Support Vectors is a AI training and R&D organization. We do three things. We train people in AI, people who want to come into this field or develop expertise on any of the topics. We do provide training in that, and this is our course portal, supportvectors.io, where we offer a lot of courses. They're just starting, or they have just started. It's still a great time for anybody who is interested to join us. These are very hands-on courses that you take. You will have access to hardware worth hundreds of thousands of dollars. You'll have root access to work on those, which is one of our big features that we provide. So it's a great learning atmosphere. Other than that, we do, of course, the usual product development, and we do also consult and help companies, give advice to companies. So that finishes my little 1 minute spiel about the company. And now coming back to the paper, the topic today, we're continuing a series. We talked last week, to give you a perspective, we talked about this paper, which compared to today's topic might seem a little unrelated. We talked about a paper called Colbert, or a topic called Colbert. What it said, and just to summarize what it said that instead of doing text embedding using a single vector into a single vector, which is what people do, like, for example, most RAG implementations these days, most text embedding implementations convert chunks of text into a single vector. Colbert, and it's usually spelled as pronounced not Colbert, but Colbert. Colbert takes a slightly different approach. It says, let's not do that. One vector is insufficient to capture the entire semantic essence of a chunk of text, especially if the chunk of text is somewhat longish. Let us instead store a family of vectors, a bag of vectors for each document. You do pre-compute those vectors, you save it into the database, into a vector database for what you need. Then when a query comes, likewise, you decompose, you pass the query through the same encoders, and you get again a bag of vectors. And then you look at max similarity. There's an equation that does a relatively fast, but still computationally a little bit more expensive compute compared to the traditional single cosine distance, one vector comparison. You do it with these documents and retrieve the documents. The results speak for themselves. The results are very, very impressive compared to the traditional vector embedding. That very impressive, actually. And more and more people are realizing that perhaps this is the right way to go. And people have been hammering at it to bring down the cost of compute with great success. We'll keep this as a background, and we will switch to what may appear to be an unrelated topic, namely PaliGemma, a model called PaliGemma. And it is leading somewhere. Why would we flip to an entirely different topic and say they're part of the same chain? We have Colbert, PaliGemma, and then the next paper that we'll read next week is Col-Pali, which sort of brings these two ideas together, right? In a very interesting way, and Col-Pali is getting a tremendous amount of attention these days. It's a really very good model. So, and I thought that the best way to get to Col-Pali is to do the background work. These two independent streams of thoughts or rivers of work, research, come together in that. So we are now looking at the second stream, namely PaliGemma. So PaliGemma itself, we will start reading now, is a composition of two research papers, two streams of research in its own right. There is first, give me a moment and I'll pull the writing board closer to myself. There is first Pali, and then there is the other stream, Gemma. So what are these two? Pali is something perhaps is new to you, but Gemma you probably have heard of. So I'll talk a little bit about Gemma. These days, there is a push to have smaller models that try to achieve the same level of efficacy as much bigger models, much bigger cousins of theirs. So, for example, can you build a model that is just 2 billion parameters in a world in which most models are 3, 400 billion parameters? Could you come within shooting distance in performance to a much bigger model? Can you take a 2 billion model and try and aspire to make it at least as good as a 70 billion or 100 billion parameter model, or perhaps come to within shooting distance of a much, much bigger model? And this whole tradition has been gaining a lot of attention. Gemma is the Google effort. It arises from the Gemini. It uses the same research, the same architecture, I'm told, that is Gemini, but scaled down, right? And it takes a different path. While Gemini and all these commercial models are they're getting bigger and bigger. So why bigger and bigger? Because it turns out that there's a neural scaling law which says the bigger the model you take, the more the data you train it with, and the more iterations that you train it for, the more performant, the more capable it is, and it may even have more skills, new skills that smaller models don't have. Now, there is a contrarian train of thought, and there are a lot of works. For example, one of the early works was the classic paper. Now, well, we would call it classic, of Microsoft, called a textbook is all you need, which basically said you could take, which started the whole 5 series. And I believe just recently 5 3.5 was released with impressive results. This is the world of small language models. They say, what can we do besides just scaling up a model? And they uh, try to look at all sorts of things that will sort of make it. Why is it practically relevant? Small models are things you can put on, for example, your cell phone, your mobile devices. They could walk around in your pockets, in your wearables. They can walk around on your laptops, in everybody's laptops. They could embed them potentially as a little library on everybody's system without their even worrying that they need a big AI stack to run. So the small models are getting a lot of attention. One way that the small models do well, for example, the message in textbooks is all you need paper, was that give it high quality data. All data is not the same. That if you give a better, cleaner, nicer, more semantically rich data, you basically get a small model to do very, very well, right? Not quite as well as, for example, you can make either Cloud's Sonnet or GPT-4o or any of those things to do, but still do surprisingly well given its scale. So, in other words, it is boxing way above its class, right? Or delivering performance way above its class, right? And it's almost like you take a featherweight boxer and is now competing with a heavyweight, right? That's the promise of doing that. And obviously the implications are enormous if we could do that. Tremendous. Most in practical terms, most of us are sitting. I'm sure if you're doing this, if you're doing it on your own, you have a 4090 RTX 4090. If you're working in corporations, at most you have like your department. While companies are huge, for development work, your department probably has access to one or two H100s or A100s. If you're really lucky, your team has enough cloud. You probably have access to one server with 8 A100s or H100s embedded in it. But that sort of represents the limit of what you can do. So obviously, a lot of us are just sitting on the fence observing while the big guys with their big hardware are happily going about writing research papers. And surely we would like to have a place under that sun, be able to play in the same grounds. So, in that sense, these small models are vital, and people are doing a lot of things to make them better. So, that is the narrative about Gemma and all these small models, Phi, Gemma, etc. Now, what is Pali? Pali is a multimodal architecture, very much like Lava. For example, you could ask a question, you could give it an image. Okay, this is too fat. Okay, you could give it an image. I could give it an image of let's say, a dog, Well, my dog doesn't quite look like a dog, but it is, right? With big ears. So here's my dog, and you can say, what what is this fellow doing? And then out would come an answer saying, this dog is playing with the ball. Let's put a ball here. Playing with the ball. Right? So you could do things like that. These are multimodal languages. Or another classic task is captioning. Right? You can give it a caption. You could do that. Now, if you remember, we have models that do that. We have, for example, and in this series, in this meetup series, in the past year, we have covered models like Blip 2. If you remember, we started this entire series, Clip, Blip, Blip 2, Lava, which are all visual language. We call them VLMs, visual language models. Um, these are all visual language models, VLMs. Right? This is the world of VLMs. It all, I mean, one of the, obviously, Clip itself has predecessors, the Vertex and other things convert. But Clip was represented a milestone, if you remember, that you could, it enabled multimodal search and many, many things. So I would say that this Pali is in that same tradition, but it departs from the usual in a couple of remarkable ways. So I would explain this paper by saying two things. What PaliGemma does is that it has a few key contributions, but amongst its core contribution is it says, let's see what Pali did, but let's do it with a much smaller model. So the whole question is, what was Pali? So Pali itself has gone through evolution, Pali 1, Pali 2, Pali 3. But before I go to that, let's see what a typical language model used to look like. A typical language model, if you remember, used to look like this. You would take an image encoder. By image encoder, think just either directly a VIT, or you could take a clip and feed it in, uh, and you would take a large language model and you would give it some queries and text and train it. You would put a Q former in between. This used to be, and I won't go into that. If this doesn't ring a bell, then that's perfectly fine. But at the end of it, you would take the crucial thing that I want to point out, and where Pali began to differ from those is the fact that you could, do you notice that snow flake symbol, the frozen, that you would take off the shelf encoder, you would take off the shelf LLM, and the only thing that you would train in those models used to be, the only training part used to be just the Q former, which used to be a much smaller model, and you would train a much smaller model of a few 100 million parameters, not even a billion parameters. And you would get very effective visual language models. Right? This is the BLIP2 evolution. Now, likewise, you have Lava, but I won't go through all of them. I'll go straight to Pali 3 because it's a long evolutionary journey, as all research work is. It goes in small improvements and big improvements. So Pali is putting together. So one way to look at it is, what did Pali do? Pali is best explained with this image. So let's look carefully at this image. I don't know if it is visible, but I will just make it this picture bigger. So there is a guy sitting in a hammock and taking, in a way, a picture of the beach, right? And his own feet or her own feet is visible in the hammock. The 2 feet are visible in the hammock. So the idea with this is you once again, in typical, just like visual language models, you give it a question: where is the photographer resting? And the if all goes well, a nice, well-behaved model will say, "Ah, in a hammock under a tree on a tropical beach." Right. So that is visual language model in action. Now, And this little bit about this, we are all familiar with the standard clip. I just not use the word clip. But here you don't see the word clip. You instead see the word sig lip. What is sig lip? One of the discoveries that happened over the recent past is this. So let's go back, and this is a very quick recollection of how a clip used to work. What would you do in clip? It was a contrastive learning. CLIP stands for contrastive loss, image, retraining. These two words are sort of implicit. So let's focus on the contrastive loss. You would send an image, as in the standard, chopping it off and so on and so forth. You would produce your VIT kind of a activity. You would produce a text through a BERT-like encoder, and you would get the same embedding. You would project it into the same d-dimensional vector space. Now you have an image object, I, you have a text vector, and what you would do is, if the text relates to the image, so you would create the triplet pair, typical contrastive loss, image that is meaningful, the text would be the actual caption of the image. How would you get the caption of the image? It's very hard to sit and label billions and billions of images. Well, it turns out the web developers have done that service for you. You just go scrape the web, and in web, you notice that they have the IMG SRC, SRC is equal to blah, blah, some image. And then there is a alt field which contains the image. It is not always perfect because people often use the alt, either don't give the alt or they sort of SEO optimize it. They'll stuff it with keywords to attract traffic to their website. So there are all this sorts of mischief happening. So the data you get is a bit noisy. Nevertheless, you still end up getting data. You end up getting images and captions that are aligned as training data. And then you can just put in some random stuff. So now what do? You write a loss function, a contrastive loss that maximizes similarity. Let's say you do, just to oversimplify it a little bit, you can say maximize the cosine similarity between image and caption, and minimize, right? Minimize the cosine similarity between image and this random junk, right? Which is the same as saying loss is max cosine of caption, image and caption, minus max of cosine of image and random, because minimizing something is the same as maximizing its negative. And that is your classic triplet loss. This, if you look at it, is the classic contrastive loss. Right? Now, if you were to convert it to probabilities, the same equation, we could write it as probability of image and caption. The probability that they are the same should be high, right, which you can do, and the probability that image and random should be low, as low. So you can also write it as a sort of a log probability. Log. So you do this as you know, you can write it as a log loss for negative log likelihood of probability. When you write it like that, which is sort of the caption, what's the probability that these two are similar? Now, what the SIGLIP papers said is that typically when you find out the probabilities, you tend to use softmax, right? The softmax function, which was very, very common. And it just said that replace it with, don't use softmax. Just go back to your usual sigmoid loss. Right? The paper has a little bit more technical depth, but it was a surprise that if you could just replace your softmax with a sigmoid loss, and there's a bit of technology how you do that, they found that the clip itself, with just that one replacement, basically that one core replacement, does far, far better. Right? And so now, so in other words, you can think of SIGLIP as just a better version of CLIP. Or it just does better contrastive encoding. And to summarize it, it does a contrastive loss encoding of images. Right? So that is the SIGLIP. That is why in this research paper, in the Pali research paper, you see the mention of SIGLIP. So what will it produce? At the end of it, and that's the word that you see here, uh, contrastive vision encoder. I hope we now understand where that magic word contrastive vision encoder comes from. Right? You have encoded this using a contrastive loss. Somehow you have to train that. So what will it produce? All encoders produce vectors, right? So let's say 10, a whole vectors. And what it says is that don't do mean pooling or anything. Don't pool it back into a single vector, average it out or do something max pooling, whatever it is. Just mean pooling. Instead, leave them as vectors. So what will happen is that image will become a bunch of vectors. Uh, Let me use a different color here. Image will become a different vector up to this. And then when you take a text and you go through the same process of tokenizing it, what will this become? This token, it will have its own vectors, text embedding vectors for the tokens, token embedding vectors. So just put it together. Now you have the image. The image has gone through this fancy contrastive vision encoder, think SIGLIP, literally. And then text has also become tokens. You put the two together, just concatenate them. And what you do is then you pass it through in the original Pali papers or the Pali 3, you pass it through UL2. Now, universal language encoders or universal language models for things were full transformer models, as in the attention is all you need sense. You remember with the full encoder and decoder. Now you know that there are three kinds of transformer architectures you can create. You can create an encoder only architecture like BERT. You can take from a classic attention is all you need sense. You can take a decoder only architectures like the GPTs, and most of these generative models are decoder only. And or you could have one with both. Right? For example, BART and so forth, T5, FLAN, and so forth. These are all they are full transformer encoder decoder put together. What UL2 was in that tradition, both of them put together, but they used something, a process of, and I won't go into the technical detail, a mixture of denoisers internally, some way of separating out specialized skills that the machine could develop, right? Language skills it could develop. At this moment, it's not relevant for our current paper, but suffice is to say that when this paper was written, people thought UL2 would be a great idea, use that. And when they did that, it all worked. Now, now one more thing is there. When you take these two tokens, they might come out as different dimension. The typical way that people do to bring it to the same dimension is they pass it through a MLP or something like that. Or in the very simplistic form, you can just use a matrix to project it down to the same dimensionality. But that is it. So I hope this becomes clear. What you do is, if you look at this part, and I can let's take another line, blue. If I were to look at this blue world, this world, what you're doing is you're taking image, converting it into tokens in a smart way. And when you do contrastive vision encoder, it is semantic meaning aware. And when you pass the text and encode it, of course you encode, just tokenizing and creating embedding vectors. At the end of it, when you concatenate them, what do you get? You get a whole bunch of vectors in a line, right? Token vector, token, whether they're visual tokens or word token vectors, they are vectors. Downstream to the right of this blue area comes a model that doesn't know where it came from. Now, there is an interesting observation. What it means is that you can have cross attention as it goes through the transformer encoder and decoder A visual token could be paying attention to a word, and a word could be paying attention to a visual token, isn't it? Because it's fair game. Like, how does attention work? If you give it a sentence, every token can pay attention to every other token, isn't it? So they can actually figure out uh, and learn from each other, or pay attention to each other. And so this model was fairly successful. So this is your Pali, and this is the third incarnation of Pali, Pali 3 vision language models. It is why would they call it small? Because as this picture shows, they were actually using SIGLIP, only a 2 billion parameter model, and a ULM2, that is a ULM2 transformer, which again is a 3 billion parameter model. So small models, right? A total of 5 billion parameter model, which is still be considered fairly small, and you still had a very well performing visual language model, really well performing. And then, of course, they made a bigger and bigger versions of this. Now, that brings us now to the current paper. If we understand that, we now can go over the current paper in depth. What this paper is saying is that, you know what, more and more people are realizing that let's not do this full transformer encoder, transformer decoder. Right? It is still too big. These days, there are ways to just make a decoder only architecture do quite well. So let's replace that with Gemma, which is a pretty good recent model. So folks, when you look at this image, I hope it is reminiscent of the other image. Right? Exactly the same picture in this paper, PaliGemma. If you look at the blue part, like what I had initially colored blue, uh, if I were to recolor it, you would not know that I have switched from one paper to the other paper, isn't it? And you notice that even your SIGLIP has become even smaller. It has become a 400 million parameter model, not even a 2 billion parameter model, right? So they took a very small vision model, contrastive vision encoder. Now comes this question. See, when you take text, where is the photographer resting, and you tokenize it and you create word vectors, its dimensionality may not be the same as the dimensionality of the vectors, token vectors coming, visual token vectors coming from the SIGLIP 400 model. So you need to change the dimensionality. There are two ways of changing the dimensionality. The simplest way is just to use a projection matrix, just weight matrix, do that. So for example, how would you project a three-dimensional vector into a two-dimensional vector? Multiplied by 3 by 2 matrix, and you'll get a two-dimensional vector, right? So that is a linear projection. The other is not just do linear projection, throw in some distortions, some deformations, put in a full MLP there, multi-layer perceptron there, a few layers of feed-forward network there, right? What they found actually is that it is best to just do a projection matrix. Simplicity. I suppose the main message of this paper is sometimes less is more. You can get away getting very good results, being more thoughtful about how you go about doing things and keeping things simple. So you take a linear projection matrix, you get the same thing. And the other change that happens is here, you don't take a full encoder decoder transformer in the attention is all you need sense. You just take a modern, these days, Gemma, you know, these generative models, these causal models are very popular. And one of the recent things that came out is Gemma, which has been going through its generations and getting better and better. You just throw in Gemma, and which is a minuscule model, 2 billion model. And notice that this 2 billion model and this 0.4 billion model just makes a 2.4 billion parameter model, which is half the size of Poly 3, right? So you have actually something smaller. And yet, as this paper argues, you end up with pretty good results, right? So now with that as a sort of an overall background, let us go and read this paper. I will read the abstract. Again, it's a Google DeepMind paper with lots and lots of authors. Um, that you see here, and a great credit to all of them, I suppose. PaliGemma is an open visual language model. Open source. Open. Visual language model, now you know what that is based on the SIGLIP SO, a 400M vision encoder. By the way, that is a vision encoder that's really optimized very well despite its very small size. So here, one of the goals was to keep the size as small as possible. And the Gemma 2B language model. Gemma 2B is, I believe, as small a Gemma as you can give. Right? So think of it as the baby Gemini. It is trained to be a versatile and broadly knowledgeable base model that is effective to transfer. What does that mean? The when you effective to transfer what? Transfer where? What they're talking about is actually transfer learning. The idea is that if you build a model or you pre-train it or train it, then you can further fine-tune it for specialized tasks. You can say, let's make it good for visual question answering, or let's make it good for this or that task. You could then go about picking your tasks at that moment. Give me a moment. Right. So you could go about doing different things with it and further fine tuning it. To fine tune a pre-trained model is transfer learning. Right? You take a model that has already been trained and then you specialize it for your task. And it is saying you can do that. It achieves strong performance in a wide variety of open world tasks. But remember, with the necessary fine tuning. But one of the things they do is, even in the pre-trained base, sometimes in one of the versions, they pre-train it with a mixture of tasks so that it becomes a general purpose one that people can download and play with. We evaluate PaliGemma and on almost 40 diverse tasks, including standard VLM benchmarks, but also more specialized tasks such as remote sensing and segmentation. Segmentation is telling in a picture that this is a tree, this is a pot, this is a dog, this is a this, and this is a that. When the ability to tell that is segmentation, putting masks all over it. Now let's read this paper and introduction. It's a fairly well written, it's a very well written paper actually, and like typical papers coming out of DeepMind, really easy to read. PaliGemma is an open model continuing the line of PaliVision language models in a combination uh, with the Gemma family of language models. Pali is a series of state-of-the-art vision language models, starting with the first Pali showing promising scaling results up to 17 billion using classification a pre-trained VIT. So if you think of the standard, VIT is the standard. Remember the famous 16 by 16 paper patch. Pixel is worth a thousand words or some. I don't know. The famous VIT paper using those were for what? Those were encoder models. So you often call them classification. So I'll read the sentence again. Pali is a series of state-of-the-art vision language models, starting with the first Pali showing promising scaling results up to 17 billion using a classification pre-trained VIT and MT5 language model. What is MT5? It again belongs to the family of the full transformer as an encoder-decoder. Right? A Pali X, I suppose X here stands for extra big, right? And Pali E, I don't know, E, is perhaps even bigger. Then push this further, combining VIT 22 billion and a 32 billion UL2 language model on or the Palm 540 billion parameter language model. So you notice this, guys, that Palm X and Palm E, the Pali X and Palm E, they were pushing the boundaries by going bigger. Right? Even the VIT became 22 billion parameter. In the visual visual encoders, 22 billion parameters is quite big, right? And a 32 billion parameter universal language model, UL2, those are big models. And while you're at it, why not go even bigger, 540 billion parameter Palm? Right? Palm is one of the state-of-the-art Google models. So they tried that and getting a further increased performance on vision language tasks, albeit saturating performance on standard image classification and retrieval tasks. So what they say that when you do this for visual language, task, which is multimodal task. Like you have a picture, you ask it a question, or you say caption it or do something. Those tasks it did very well when you scale it up like that. Scaling, you would expect it to give good results simply because that is the neural scaling law, isn't it? That quite literally is how neural scaling works. Laws work. Bigger, better. So great. But they also notice that for just standard classification and retrieval tasks, encoder-based tasks, your results saturate. Getting bigger and bigger doesn't really buy you much. So then they say, finally, Pali 3 demonstrates that through better pre-training with SIGLIP and more careful multimodal data curation, a 2 billion vision and 3 billion language models match the 10x larger PaliX and 100x larger PalmE across most benchmarks. So they said that they had a turning point when Pali came out. The previous Pali, as we saw, was a 2 billion vision model and a 3 billion UL2 universal language model that you did. Relatively smaller models, but the main thing is you benefited from a better loss function. Remember SIGLIP we just talked about? It used a sigmoid loss function. Just by doing that as a contrastive loss function, you got to scale it down by 1 or 2 orders of magnitude and still get just as good results, which is amazing. Right? And just be more careful with the data. Have cleaner data, which is a message that is resonating quite well these days. People are finding over and over again that the quality of data, perhaps in hindsight, unsurprisingly, has quite a profound effect on the performance of the model. And it is as vital as just what performance gains you'll get from merely scaling up the model. Right? So it continues that. PaliGemma continues this trend, combining a 400 million. So I will deliberately rephrase it as zero point 0.4 billion SIGLIP and a 2 billion Gemma models, these two pieces. So you're going even smaller. So it gets you into a sub 3B VLM that still maintains performance comparable to Pali X and Palm 3 and Pali 3. So let's think about it. You have created something that's smaller than 3 billion parameters, and yet it's competing with the likes of a 100 billion parameter model. That should be surprising, right? That should be really, really, or no, 540 billion parameter model, PAMI, right? Some massive models. So how do they do that? The whole question is, okay, that's very impressive results. How in the world do they do that? We'll learn about that. Gemma is a family of autoregressive decoder-only open large language models built from the same research and technology used to create the Gemini models. Basically, they're saying it's a baby Gemini. The models come in different sizes, 2 billion, 7 billion, both pre-trained and instruction fine-tuned. Because why instruction fine-tuned? Because these days, one of the dominant use cases for is chat, right? Conversations. So PaliGemma uses the 2B pre-trained version. The main goal of our work is to provide a versatile base uh, VLM. Hence, be sure that it reaches state-of-the-art results not only on standard COCO captions, VQ, blah, 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 and infographics, etc., but also on more exotic remote sensing VQA, that's on remote sensing data images, and etc., etc., video captioning and so forth. As we'll see, it can do video captioning as a zero-shot learning exercise, but that comes later. I'll just skip over the related works and go straight to the model. The model we have talked about, but let's go straight to the architecture. Architecture consists of 3 parts. Image encoder, for which we use a publicly available SIGLIP, which has been specifically shape optimized. So there's a bit of an effort. People have found that if you shape optimize, if you're very careful about the internal shape of the transformer, you do get pretty good results. It goes through the same contrastive pre-training as CLIP, a decoder-only language model. So guys, the architecture I've already explained. This is the architecture. We need not dwell upon it anymore. The important thing is it uses a linear projection SIGLIPs of the SIGLIPS output into the same dimensions as Gemma 2B vocabulary tokens, so they can be concatenated. So they can be put together. And the important statement they make, which again is worth mentioning, is that In early experiments, we found that more complicated alternatives, namely full-blown multilayer perceptrons, do not provide a clear advantage, and hence decided to use the simplest option. Then the image is parsed through the image encoder. The picture makes it very clear. The important thing is they did this training with three size images: 224 by 224, 448 by 448, and 896 by 896. In other words, low, medium, high resolution images. They were all square images, right? And then there's some padding, separator, etc. The one interesting thing is they are not using masking, like as you know, which is clear from this picture. So it was the point that any of these can look around. They can all look back and forth across the multimodal landscape of tokens. They can all peek at each other. The only thing you mask, which you have to, is the output generated tokens, the suffix. So by the way, this paper uses a very Google-ish language, Google specific, like what you would call prompt. In this paper, they call prefix, the old way, right? So remember, prefix is just prompt or input, what you would call input to the model. And what the model produces, right, the output, they call, when they use the word suffix, it is just the output, continuation, result, whatever you want to call it, what comes out of the model, right, from the generator of the model. So they keep using prefix suffix is their way of saying. It's a more formal way of saying the same thing, but it is what it is. Now, the training is done. The people use the word pre-training because the general idea is that once this model is trained and released, it is actually a pre-trained model. Now you can do whatever you want. And they wanted to emphasize that it's open to further fine-tuning. Like the purpose of this model is that you take it and now you adapt it to your specialized use cases. Right? So it's very domain, it's very transfer learning ready model. They didn't want to make, for example, when you just take a model like, let's say Llama, or you take Mistral or something, it has been, in many ways, you can say that it has been trained on a heterogeneous uh, sort of tasks to be versatile. Whereas these people did not shoot for versatility. That is a crucial difference. They didn't want to make a model that's good at everything, equally good at everything. You can't do that, you know, it's a small model. So what they do is, what they say is, we're giving you a model that is optimized for fine tuning or transfer learning. You can then adapt it to whatever use case you want to do. How do they do that? The training actually goes in 4 stages. And these words are worth knowing, and I will sort of highlight it. There is unimodal pre-training, multimodal pre-training, resolution increase, and transfer. So I'll give a very quick explanation that they've given. In unimodal pre-training, you just train the visual encoder, the contrastive, and so forth, right? And if you want, just train that. It's simple. Multimodal is where you bring the two together, right? You train uh, this model together with caption and this, and then resolution increase. Okay, what you do is you train the model first with low resolution images. Once it is trained, then you start feeding it bigger images and then bigger images. They found, and this is a practice very often done in the visual language domain, they have found that it helps. Systematic learning leads to much better results, right? And a transfer, that's a resolution increase phase. And the transfer part is that now that you have a base model, they take a slew of specialized tasks and they fine tune the model on those specialized tasks so that you end up with a slew of new models, with each one of which is good at one particular task. And while they're at it, just so that people could use something out of the box, they also take a mixture of tasks and train a general purpose model that is reasonably good at variety of tasks, whereas that was not their goal. I mean, that was not the primary goal. So you go with stage 0, unimodal training. Now here is a crucial difference. Typically, when you do clip, or when you do things like that, in the visual language models, you would just take a frozen. We just saw in Blip 2, for example. What do they do in Blip 2? You notice that I mentioned they take off-the-shelf image encoder, don't touch the weights. It's frozen. Just use it. Don't. Only thing you train is the Q former in between. The large language model also, don't touch it. Right. Let the weights be frozen, and you just train it to do train the Q former back and forth through training data. And that has been the prevailing wisdom in this space. But PaliGemma and these people, they actually say, no, let's op- open it up. Why would they not do that? Because prior experience had shown, or the prevailing wisdom was that, for your task, if you open up the visual encoder, right, that you take and open it up, all the weights, and you tune it on your task, what you will notice is that you will actually not only not make the model better, you will actually screw it up. Right? Its performance will actually go down. Now, they actually found that that is not the case. Recent research has been emerging that says that if you do it correctly, it doesn't happen like that, right? You don't need to do that. So let's take it like that. We'll read through this. First, the unimodal components of the model are pre-trained individually in order to benefit from their well-studied and scale-trained recipes. For PaliGemma specifically, we do not perform any custom unimodal training, instead rely on existing publicly available checkpoints. Following Pali 3 strong experimental results, we use a SIGLIP image encoder. Just think of it as CLIP, better version. While Pali 3 and others use a large image model, such as VITG, we use the much smaller, and the emphasis is on the word much, much smaller, but similarly strongly shaped VIT SO 400M, just a zero point 0.4 billion parameter visual model. Tiny, tiny, tiny. Okay, Pali traditionally uses an encoder-decoder language model. However, all recent public release models are decoder-only transformers. So we know that. The jury is out. People have found that for text generation, decoder-only models seem to be ruling the roost. So it's time to go with that. We opt for the Gemma to be, which strikes a good balance between size and performance. Larger models such as popular 7B or 70B size are often significantly better at tasks like mathematical reasoning. They say that why? Because what they found is that yes, bigger models are better because of the neural scaling laws, but they're better at things that perhaps is irrelevant for this visual language model. They're better at mathematical reasoning and so forth. We are not doing that here. However, Pali 3 has shown that across a wide range of visual language tasks, a well-trained small 5B model can do just as well, right? Compared to the huge, huge models. We won't go into that. So stage one, multimodal. So the stage zero is just go take a unimodal pre-trained model, in particular SIGLIP, and go with it. Take a tiny one and go. So now comes the real work. So picking one off the shelf is as simple as, 5 lines of your Python code, perhaps. But now comes the real stage one. In this stage, we combine the unimodal models, as explained in blah, and train the whole model on a broad mixture of large-scale vision language tasks. And now the crucial statement. Contrary to most recent VLMs, is our goal is to train a base model that fine-tunes well across a variety of tasks. So in other words, goal is not to create a model that's already versatile at everything, but to create a model that is great for transfer learning, to be further fine-tuned for different tasks, which is a very wise decision. Ultimately, it's a small model. Right? So it can perhaps do one thing well. Intuitively, we want a mixture of tasks which forces the model to acquire a broad range of skills, regardless of the task's user friendliness out of the box. So in the beginning, you can fine tunes well too. So what happens is that it's a good at a variety of tasks, but not perfect at it. It has those skills, but it leaves perfection to be achieved through fine tuning. It is common practice also, uh, it, following pre-trained versions, to keep the image encoder frozen. So this is it. This is another departure from the norm. Right? They say that previously you would take the image encoders, and obviously here they mean contrastive image encoders, frozen during the multimodal pre-training stage. Here they take this unlikely step of opening it up. So this is partially due to findings as in LIT reporting multimodal tuning of pre-trained image encoders degrade their representation. So that is the danger. People thought, don't do it, you'll just screw it up. And so that used to be the prevailing wisdom. Now they go on to say something different, which is worth changing the color for, I suppose. However, more recent works such as this and others, hard to learn task can provide. The problem is when you take those models like CLIP, etc., they're not very good at spatial um, relationships, right? And spatial depth and things like that. There are certain things that they actually perform poorly at. The idea is that let's open it up. So here, hence again, in the spirit of learning more skills during pre-training. So they said that we're trying to make a model which knows more skills, may not be perfect at them, but more skills. So uh, during pre-training, we depart from common practice and do not freeze the model. This word is means you open up the weights, right? However, the challenge outlined in the challenge does remain. You can still have a risk of degradation. So in order to prevent that, they use a very clever trick. They know that really well-trained visual model can degrade if you do multimodal training and open up the weights. So the trick they do is they say that, see, when you're training the entire model, the decoder and the encoder, you don't train at the same rate. Uh, in the beginning, there'll be big gradients because there'll be big losses, right? Big errors in the early stages. Errors are huge, the gradients are big. So then what happens is the decoder losses will come and make huge impact on the image transformer. What you really want is that the vision transformer should go through very small changes, small adaptations, right? You want it to pick up new skills, not lose everything that it knows. So for that, what you do is that you use a slow linear warm up of the image learning. So this is again goes back to the scheduling rate of the learning rate, the scheduler of the learning rate. How do you do it? So you give it a very slow linear warm up of the image encoder learning rate. So basically you go like this, and then of course eventually you'll go down. The learning rate will go down. I suppose somewhere there should be an image either in this paper or the prior paper. I think this is what yeah, this paper itself somewhere it should be. Oh yeah, here it is. This is it. You see a slow increase in learning it, warm up, and then the usual decline, because you do want the learning rate to come down as the machine begins to learn. So they do that, and it turns out that if you do that, then you don't screw up the transformer, the vision part of it, vision encoder. So then comes the stage two. Stage two is that you first make it learn the broad things, bigger things, like use low resolution images. So it understands the broad structural visual semantics. And then you give it more higher resolution images, medium resolution images, and then finally higher resolution images. So it turns out that systematically doing it like that and scaling it up is a very structured learning process. It's almost like you're putting this model first through kindergarten, then through, first through elementary school, then through middle school, and then through high school, right? Progressively higher knowledge. Right. And the last stage, of course, is the one that is crucial. It was designed for transfer learning. So now they are saying, okay, here is a model. Now the last stage, take a bunch of tasks and now let's fine tune for those. Transfer learning, right? The results of stage 1 and 2 is a family of 3 PaliGemma checkpoints at blah, blah, blah. However, these checkpoints are not user or benchmark friendly. In other words, if you take this model, it's reasonably good at multiple tasks, but the state-of-the-art models will beat it hands down in any one of those tasks. So then what you do is you take copies of this model and fine-tune it, that's transfer learning, for each of those benchmarks or each of those tasks, and then see what happens. They do that. The rest of it's hardly worth mentioning, but the results are fairly impressive uh, results. So let's go straight to the results. Uh, you can go through all of this. You realize that suffices to, there are a bunch of numbers, but suffices to say that uh, it does very well. Right? Let's put it this way: it does very well. And as the ablation studies show, they find that the approach they took was meaningful. In fact, one of the most sort of surprising things they did is they unfreeze the weights during multimodal training. So what happens if you don't, if you keep them frozen? You can clearly see in this picture that, look at this scale, is how bad it does if you keep weights frozen. So compared to this model in the ablation study, they point out that based on the percentage of or the fraction of the things that you do, you have worse and worse performance. Right. So you it was worth doing it. The other thing that you may ask is, was the sig like do you notice that there is an asymmetry in this diagram? You have you took the tokens and you made them into embedding vectors using the Gemma encoder, right? The text tokens. Text becomes just directly into embedding vectors. But the image went through a full blown sophisticated model, SingLip, and became tokens, right? Finally. What happens if we remove that? Is it really necessary? Why this asymmetry? And obviously, they confirm that it is necessary. Otherwise, you would have pretty bad performance. Right? Uh, Raw patch encoding versus a PaliGemma, then obviously you do need it. It's not that you can't. Which one would have imagined, but it's worth doing that ablation study. So this is the image encoder with or without. Uh, it talks about it. And then increasing resolution has two effects: increased information content of the image input and increased model capacity by sequent length. For tasks that benefit from increased resolution, both of these effectively contribute roughly equally to the overall gain. So it's good. Uh, there are different ways of increasing resolution. So we won't go into all this uh, fine details. Uh, but generally, because at the end of the day, let's stay with the bigger picture. What is the message? Let's step back and say, what is the message coming out of this thing? Let's read the conclusion. It's very simply and powerfully stated conclusion. It says Poly is a new small open-based VLM that shines when transferred to a broad range of tasks. The operative word is shines when transferred. It doesn't say that you can take a generic model and it will beat every benchmark for every task in one instance. Our results show that VLMs on the smaller side can provide state-of-the-art performance across a wide range of benchmarks. We also hope that providing the base model without instruction tuning serves as a useful starting point for further research and instruction tuning, specific applications, and encourages clearer separation of base models and fine-tunes in VLMs research. Right? So that's a bigger model. And then how did they train it, etc., is a prefix, etc. The appendix goes into this, but there are no surprises there. Like it's just you would expect it to. So here's, for example, a training data. If you want to caption, you want to say, look at this picture, and the caption that you give it, a man washes pots and a cutting board. Or then this one. And by the way, they trained it on images as etc. And one of the things they notice is that it does quite well on videos too. What is the person in the video doing? So for example, here, what is doing? And the answer is bathe the dog. Suffix is that. And you sort of train it with data like this, simple data. Now, when you use PaliGemma, there is a website. If you go to Hugging Face, there's PaliGemma has a website. Let me see if I can find it. I usually work on my Unix machine, Linux machine. This machine, Windows machine, I only use for teaching because Unix doesn't support my handwriting board. So I hope I can find the PaliGemma. Let's try and see if we can find the PaliGemma. Yeah. And have they given a demo? PaliGemma model, but Pali uses the SingLip. Okay, that is fine. There's a demo somewhere. Cookbook repository, learn more. No. PaliGemma. Okay, yeah, maybe. Let's try that. PaliGemma. Response card. No, it takes you Kegel. Let's go to a Hugging Face. Hugging Face has that, I think. Um, oh, there it is. So there is a notebook that you'll have, PaliGemma, and as a text. No, there is certainly a demo here somewhere, and you can see. But till we can find the demo, I can just speak
It is
to
on
it.
Hugging Face, they say.
This is Hugging Face. We are in Hugging Face. We are on Hugging Face.
Okay, okay.
To be. So I think we'll come to it. You
There
can
is a,
find
I
them.
put a link there if you want to take a look.
A link where?
In the chat.
In the chat. Okay, 1 second. Uh, oh, there we go. Thank you. So we can upload an image, or we could just look at, let's take any one of this thing. So when we look at this, obviously, we see that there's a broken branch here and things. And the question is, what caused this? If you run it, now you can pick from the models. You can pick a high resolution model or greedy, different decoding. This is your sampling strategy at the very end. But what I observed is that very much like the training data, it tends to, as a base, let's try this. And it says storm. Do you say how the brevity of its answer? So that's something worth observing. But it can be made to give slightly bigger answers. So for example, let's run this. Here is a scene, beautiful sunset of kind, I suppose. Let's say if it gets the word sunset or sunrise. Oh, now it is descriptive. A small house sits nestled amongst a serene landscape, its red exterior contrasting with the vibrant green grass and towering hills. The house exudes a sense of tranquility with its white window frame and railing and the wooden fence that surrounds it. So it managed to catch hold of this wooden fence that seems to be there. The surrounding landscape includes a dirt hill, which is here in the background, a mountain covered in grass. I don't see that. Where is the mountain covered in grass? Well, sort of. It's like dry grass.
See the towering mountains also, actually.
Yeah. And a road winding through the countryside, which we see. The sky above is adorned with fluffy clouds. Are there fluffy clouds? Well, sort of, yes. They are fluffy clouds. Casting long shadows across the ground. The house's roof is adorned with white, and the window gets a glimpse into the tranquil atmosphere. I suppose this is what it's calling grass field. So a little bit of a error. And it seems to have not quite caught on to the fact that it's an early morning or late evening scene. Okay. So this is it with its plus and minus. This is it. So, folks, this is the reading of Gemma. Any questions before I stop the recording? Was it clear, guys? Was this paper relatively clear to understand? So this is it. This is the Gemma paper. Now, why are we doing something so entirely different from last time? Last time was all about embeddings, right? And similarity searches and so on and so forth, the semantic embeddings, Colbert. And this is about PaliGemma. They come together in the next paper. And next week, we'll do Colpali. Right? They sort of form a good continuum. We'll do that. All right, guys. So I'm going to, if there are no more questions, I'll stop the recording.
I just have one question.
Go ahead.
So essentially, they are bringing both into the same vector space
Oh yeah, all multimodals do that. All multimodal models do that.
to the query as well as
Yeah,
and then
yeah,
they would do cross attention and all of that on
that
top of
is
that.
right.
Yeah.
That is right.
Okay.
Yeah, that is right. I mean, I suppose the whole tradition started with the likes of Clip. Clip was the one that scaled it out. There were a few predecessors to it, but Clip really made it famous. Thank you.
Correct. Correct.
So, yeah, it feels like ancient history now, but it wasn't that many years ago.
A lot of people on this paper.
Yes, lot of. I mean, these kinds of work take obviously team effort. And what is interesting is, as always with good research, it represents a whole spectrum of nationalities and cultures that came together, which I find very interesting. The best works are created are global efforts.